in electron volt. So again, we can have two very equivalent statements. Angular frequency is 1.5 times 10 to the 15 hertz. Is equivalent to the statement a photon with this frequency. Oops, I'm getting feedback. Would have an energy of 1 electron volt. So we have related a frequency, which is nothing but an inverse time scale to an energy. So frequencies and energies are treated on the same footing. Again, basically, we use a fundamental unchanging relation of nature. Basically, that photons with certain frequencies come with quantum mechanically determined energies. Now that we have frequencies related to energies, so we trade time or frequencies time and frequencies against energies. That's what this relation allows us. And you can continue doing all these kinds of relations using different combinations of H bar and C. For example, you can also relate masses using E equals mc squared. So that's putting the speed of light equal to 1 really basically explicitifies the direct relation between energy and mass. So energy is really mass. Or if you want, you can also do something like 2 pi over lambda equal the wave number equals the frequency divided by the speed of light is equal to something like h bar omega divided by h bar c. So you've simply added an h bar for convenience, and that of course is again the energy divided by h bar c. So we can thereby relate distances to energies, or if you want, wave numbers to energies. So doing all this and basically repeating this process for all the kind of known units, we can basically boil down everything to one unit. So basically, at the end, only one unit is left. And this can be, for convenience, electron volt, but if you want to do something else, you can do meters, seconds, joules, kilograms, whatever. Basically, the whole point is that you can measure everything in 1 unit. You can say the final result has units of energy, it has units of energy squared, or equivalent, you can say it has units of frequency or frequency squared. This sounds like a little bit of a kind of, well, on the one hand, it's very convenient. But on the other hand, it also clarifies a lot of the fundamental connections. For example, this here makes it quite clear that when we're, say, dealing with relativistic systems, that length and time should be treated on equal footing. And so basically setting c equal 1 basically makes it very clear that space-time is actually 4-dimensional. And similarly, this kind of automatically explicitifies the fundamental relations in quantum mechanics between frequencies and energies. Okay. And basically, if you want, it tells you also, if you think deeply about it, it tells you something about the measurement process itself. At the end, what can we actually measure? That's a really difficult question. Typically, if we weigh something against something else. So we are typically measuring ratios. So we are measuring the ratio between a lump of metal and a certain piece of gold stored somewhere in Paris. Okay, so that's how we measure weights. So we are typically measuring ratios of something we want to measure in detail to something we have defined to be a certain quantity. So typically we measure ratios. You could also say, instead of measuring against this block of gold, you could say, I'm measuring against so and so many atoms of a certain substance. So basically, the whole point of choosing the right units is also to clarify in yourself the deep relations that may exist between some quantities like length and time, but also to clarify that the measurement process actually typically just looks at ratios of certain quantities. Okay, but there's one more great use of looking at units, and that's also basically getting a result without doing a calculation. Checking out that your result has the right units, or what kind of units the result should have, can really tell you basically how the result is supposed to look. So you can say getting and I'll just give an example here. And maybe I should say getting or checking a result. Because checking your results when you do complications, that's something you will find out in the next few months or in the next few years when you're doing actual calculations. You will make mistakes. It happens to all of us. So the question is, do you find the mistakes? And basically, do you realize hopefully quite quickly that your result is wrong? So making mistakes is something everybody does. Probably about 50% of my first tries at the calculation are wrong. So the question is, how do you find out it's wrong? And one very simple trick is to check that the units are right, that the result makes sense. So, for example, let us look at neutrino oscillations. And the question is, what is the oscillation length? Okay, and then someone comes to you and tells you L equals E squared times 1 plus E delta M squared. And I should say that, so the inputs are the energy and the mass splitting, or the mass square splitting is given. So someone now claims that the result is something like this, minus 27 over pi energy times cosine delta m squared divided by the energy times 23. Does anyone have an idea why this guy who wrote this answer has no clue about physics? Yeah.
Cosine of a dimension-full quantity.
Yeah. So that's dimension-full. Using our new units, so that's, if you want energy squared, that's energy. So the whole thing here is energy. So that's proportional to energy. And a complicated function like, I should say proportional to energy. A complicated function like cosine never has dimension-full arguments. The argument of cos should be dimensionless. Why is that so? Well, because cos is not a pure power. And that brings us to the next problem with this result. So basically, cosine of x is 1, sorry. Oh, I have to get used to this first. Is 1 minus x squared over 2, and so on. Okay? And here you can see why the argument of the cosine shouldn't have any dimension. Because you add 1, and then you add or subtract x squared. And if x has a dimension, so does x squared. So you are adding two things of different dimensionality. And the same holds, of course, here. The different parts don't have the same dimension. We have a 1. We have energy times mass squared, which has dimensions energy cubed. And we have an energy here, which is another energy and another different unit. So different dimensions. And then finally, looking at just the prefactor or the first term, we could also say, well, it should be a length. But length is proportional to 1 over energy, as we have just learned over here. So that is a length, and that's an energy. So energy is proportional to 1 over length, of length proportional to 1 over energy. So length is definitely not proportional to energy squared. So this is very wrong. Okay. So that's the negative side. So we found what's wrong about it. Can we also easily guess the correct result? Yes, we can. And, well, we do this very simply. Length is proportional to 1 over mass. So we have two input parameters which have both, one has dimension energy or mass. So I can say 1 over energy if you want. So one has dimensions energy and the other has dimensions mass squared or energy squared. Our final result should be 1 over energy. And, well, if it's a nice result, we should at least use both of them. Because very naively speaking, if we crank up the energy, we expect that the oscillation length increases. And if we reduce the mass squared, we at least kind of have an idea that if the two neutrinos are massless or have the same mass, they don't oscillate into each other. So basically, our length should increase with the energy and decrease with the mass splitting. And from the increase-decrease, we, of course, get only some power over here and some power over there. But looking at the result, energy divided by energy squared, well, something like energy divided by energy squared actually has the right units. So that's a guess for the oscillation length. And if you check it with the correct result, you'll find that it comes pretty close. So typically, the trick is identify the important length and mass and energy scales in the system, and you can actually really guess the final result for many quantities without actually doing a calculation. And then, once you have done the calculation, you can use this kind of guess to determine basically if your result makes sense and if it's correct. Okay, so the other preliminary thing is most of what we'll do in the following is focused on relativistic quantum mechanics or relativistic quantum field theory. So just a brief recap on 4 vectors, because it's also very useful basically to use 4 vector notations. So the important point is basically we combine, say, x0 equal time. And here, I've already used that c is equal to 1, or the speed of light is equal to 1. So it's equal ct equal 1. And the 3 vector x can be combined together in a 4 vector. Why would we want to do that? Well, we want to treat time and space on more or less equal footing in special relativity. So that's our kind of fundamental idea behind it. But mathematically, as it turns out, so if we write correct 4 vector equations, or if you want, we can also do 4 tensors. Equations, if if they are correct, then they are automatically Lorentz covariant. If we have written them in a 4-vector notation. Okay, so to indicate that we have a 4-vector, we typically use Greek letters as indices in contrast to Roman letters, which indicate 3 vectors or 3 indices quite often. The spatial and time coordinates are just one example. Other examples are momentum, for example, that nicely combines and that's energy and momentum. So that gives you the relation and the combination of energy and momentum. We can do quantities like the vector potential in electrodynamics, which combines the static potential and the vector potential of the magnetic field, so to speak. So this automatically already treats electric and magnetic fields on the same footing by combining the electric and magnetic potentials. But we also have things like dx mu. So derivatives with respect to spatial coordinates, something like dx0, dx I can also form a 4-vector. In particular, we should note, and that's has to be made clear, if we take derivatives with respect to the lower components, and I'll explain that in more detail in a second, then the derivative actually behaves like a thing with an upper index. Okay, so here we have some examples of vectors. But we do not only have vectors, we of course also have a scalar product. That's something typically very useful in physics. So we have a scalar product. If you want to be extremely precise, in mathematics, people would argue it's not a proper scalar product. It doesn't have all the properties, but for physics purposes, it's a sufficiently good scalar product. What is this scalar product? If we have two quantities, two 4 vectors, A mu and B mu, we simply combine it with the 2-index quantity. Sorry, it shouldn't be mu. Sorry. A mu and A nu. Sorry about that. Is equal to, and that also defines the symbol eta, A0, B0 minus A Bi. And let me define quite a few things in this equation. So eta mu nu is simply the matrix. Doesn't depend where I write the indices. If I with both lower or both upper indices, doesn't really matter. It's a matrix like 1, minus 1, minus 1, minus 1, and zeros over here, and zeros over here. So this thing over here is called symmetric. And it basically tells us something about the properties of this 4-dimensional space. What other notation did I use here? Well, writing it completely explicit, I should write A0, B0 minus A1, B1 minus A2, B2 minus A3, B3. So I've basically already used the so-called Einstein sum convention, which simply says indices which appear twice are summed over all their values. For example, here we have mu, 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 mu. So mu appears twice, mu appears twice. So we sum over, and we sum over all their values. That means for mu, nu, and so on, we sum 1, 2, 3, 4. And for our Roman indices, I, j, and so on, we sum from 1, 2 to 3. So this thing over here is actually, if you want, a double sum 1 to 4, sum nu equals 1 to 4 of A mu, B mu, eta mu, mu. Okay. So what type of scalar product is this? Well, let's take an example of a vector. Let's put in a specific vector into this scalar product. For example, use x mu, x nu, eta mu nu, and this turns out to be x0 squared minus x vector squared is x, if you want, is t squared minus x1 squared plus x2 squared plus x3 squared. So this is more or less, so hopefully well known, invariant quantity of special relativity. So that is the distance or the length of a vector in three-dimensional space. And as you maybe know, in special relativity, we include the time and we include it with a minus. So the invariant quantity in special relativity is actually this t squared minus the length squared. And this is actually used to define Lorentz transformations. One more thing we can do conveniently with these etas or this metric, we can use eta mu nu or eta mu nu to raise and lower indices. For example, x mu is equal, or the other way around, x with a lower index is equal to eta mu nu x mu. Basically, by multiplying with eta and summing over, we can raise and lower indices. And therefore, instead of writing complicated x mu, eta mu nu, for example, we can actually write x mu. And we contract over lower and upper indices. That's, by the way, very convenient rule to check, again, if you have correct results. In relativistic notation, you should always have sums over upper and lower indices. Not too upper, not too lower, always upper and lower. Another pitfall, of course, of this Einstein sum convention is you should take care that indices appear twice at most. It's quite confusing if one index appears 4 times, because it's not really clear what to sum over. And performing 2 sums from 1 to 4 is quite different than performing 1 sum over all 4 indices equal. So basically, when doing this, one should always check that indices appear exactly twice. OK, so far we had only vectors, but of course we can also have more complicated objects with more indices. One we already had, that's this matrix eta mu nu, which has 2 indices, but there are other things with 2 indices. There are even things with more than 2 indices. So we also have tensors. And these tensors are, for example, eta mu nu, what we already accounted, but also things like the electromagnetic field strength is a proper relativistic tensor, which is given, and here you can already see the niceness of proper 4 notation, and combining everything into 4 vectors. It's given by the derivative of the electromagnetic vector potential, once derived with respect to mu, on a nu minus d nu a mu. And basically, writing the right-hand side, we don't have to check that this is a tensor. As long as we have properly used our 4-vector notation and have only proper 4-vector quantities, then the right-hand side automatically behaves like a 2 tensor. And basically, we can also go the other way. So here we have started with a vector, or if you want, 2 vectors, and constructed a tensor. But we can also go down, and basically we can also do contractions. For example, we can do something like f mu rho, f rho nu, which we can automatically identify as a 2 tensor, because it has 2 indices which are not summed over. Summed over indices do not count. Or we can do something more, f mu nu, f mu nu. So that's a tensor, or more precisely a 2 tensor, and that's a scalar. Okay. Finally, basically, I've always claimed that this is Lorentz invariant. But the trick is, of course, what has to be invariant or covariant, and what is the kind of definition of a proper Lorentz transformation? Well, Lorentz transformations are all transformations that leave our scalar product invariant. So invariant for all vectors v mu. And we want to have a transformation that somehow lambda mu nu, lambda nu, not lambda, sorry, v nu gives you something like v mu prime. And, well, to find condition, to find the, oh, sorry, to find that's an exercise for you. Find condition for Lorentz transformations. So what does that mean for the matrix lambda mu nu? Okay, so what were the important points for today? Well, units h bar equals c equals 1. That means basically only one type of unit is left. Electron volt or whatever. But the important point is also that you really practice a little bit the idea of dimensional analysis. Can be used to check and generate results and estimates. And for vector notation, basically is something that allows you to do relativistic systems very easily. Well, maybe not so special for relativistic systems. Okie doke. Yeah. Yeah. Second line from the bottom. Maybe I should erase it. So basically, the question is, or let me make this more explicit. You have a transformation. So the transformation does something to your 4 vector. So you take a matrix and multiply it with your 4 vector. That's basically like rotations in 3-dimensional space. You take a matrix that describes the rotation and multiply your coordinates by it. And here, this lambda mu nu is just this matrix describing the Lorentz transformation. And that gives you the new coordinates in the new coordinate system. And the invariance condition, maybe I should state that again explicitly, that means
oh, it's a matrix. I thought the symbol in between doesn't belong to
this one?
Yeah.
Ah, sorry. No, it has two indices, so it's a matrix. One should be careful. This is, in a way, not necessarily a proper tensor. Nevertheless, here one is typically quite sloppy and writes it simply as a thing with two Lorentz indices, simply because it's then very nice to contract. And the statement here of invariance simply means V mu should be equal V mu prime, V mu prime. So basically, if you plug in this relation into the definition over here, you already have the condition for the Lorentz transformation, how it is supposed to look. Okay, further questions? If not, then I would say see you tomorrow morning. We'll probably see each other every day now.